just on a one-way trip and not a round trip? Well, you can't use a mirror anymore. Instead, you got to use two clocks. You got to use one clock to tell you when to start the light pulse, and then another one to record when it impacts. Yes? So I'm going to stand over here. When this clock strikes noon, I send out the pulse, and my buddy's over there with his clock, and when he sees the pulse, he looks at his clock, and you're thinking that'll say, 1 second past noon. Yes? Well, I tried this in my office. I don't have a long hallway, but I have the distance between my watch and the clock on my phone, and I turned on the light right when it hit noon, and the light beam went over to the phone. As soon as the phone, lit up, I said, 12:05. It takes 5 minutes for light to get from my watch to the phone, right? No, you're not buying that? You see what I'm saying? When my clock hits noon, I turn on the light, it goes over, hits the phone says 12:05, 5 minutes. I made an assumption, didn't I? A faulty assumption. And that is, I assumed that the clocks were synchronized. Obviously, the clock on my phone is 5 minutes fast. I do that so I don't miss staff meetings. Okay? So only if the clocks are synchronized could you measure the speed of light this way. And by the way, they have to be exactly synchronized because the speed of light is very quick, whatever it is. We know it's quick. So if that other clock is just a little bit off, you'll get the wrong answer for the speed of light. It could be very wrong. You say, no problem. We'll make sure the clocks are synchronized. That turns out to be very difficult to do with clocks that are separated by a distance. Normally, the way we synchronize clocks is with a radio transmission. In fact, my watch does that. It receives a signal from the radio transmitter in Fort Collins, which is tied into the atomic clock in Boulder. And every night it receives that signal. I never have to set it. It's pretty neat. But it's not maybe exactly synchronized, right? Because that radio pulse actually takes a little bit of time to travel from the source clock to the receiver clock. Radio is fast, but it's not instantaneous. So, maybe what we could do, of course, if we knew the amount of time it took the radio pulse to travel from here to here, we could subtract that off. We could push that clock forward a little bit. Well, how fast does radio travel? You know the answer to that? It travels at the speed of light. Yeah. And so that's the very thing I'm trying to measure. That's the very thing I don't know is the one-way speed of light. We know radio travels at the speed of light because if I have a radio transmitter and a flashlight, they'll hit the wall at the same time. We know that. We just don't know what that speed is. My point is you'd have to already know the one-way speed of light in order to synchronize clocks by radio transmission. Now, I don't worry that my clock is maybe slightly behind the one in Boulder because I'm not trying to measure the speed of light. But if you're trying to measure the speed of light, they have to be exactly synchronized. Some people, for some reason, have thought if you put the radio transmitter in the middle, that'll solve it, right? Because then you send the radio pulse in both directions and both clocks are synchronized to noon at the same time. It doesn't matter what the speed of light is, but in fact it does because that presumes that the speed of light and therefore the speed of radio is the same in both directions. If it's different, then this clock gets set to noon first and that clock gets set to noon second. See, noon there and then noon there. And they're not synchronized. See, so you can't synchronize clocks that way. It doesn't work. One last resort. We'll synchronize two clocks in the same place. That's easy to do because you can see they're both reading the same time at the same time. Then we'll move one of them or both of them to opposite ends of the hallway. Yes? That should work, right? It doesn't, because according to Einstein, motion affects the passage of time. The very act of moving the clock has caused it to become desynchronized from its buddy. Now, it turns out there's an equation that can tell you how much the clock has become desynchronized, and you could compensate for it. And in that equation is the speed of light. Yeah. Isn't that interesting? It's almost as if God doesn't want us to know the one-way speed of light. Here's what the implication of this is. Apparently, it's impossible to synchronize clocks without knowing the one-way speed of light in advance. And it's impossible to measure the one-way speed of light without synchronized clocks. So you see, we're stuck in a permanent catch-22. It is fundamentally impossible to measure the one-way speed of light. It cannot be done because you need to have synchronized clocks, and the only way you can have synchronized clocks is if you already knew the one-way speed of light. It cannot be done. Now, when you have a catch-22 like this, it suggests that the question may be a bad question, a faulty question. And so I'm going to conclude that the one-way speed of light is not actually a property of nature at all, but is something that is a convention. A convention is something that we choose and we all agree to it and we stick with it and it works. Like driving on the right side of the road. That's a convention. We all agree to that, and it works. But in other nations, they pick the left side of the road. And as long as they all agree to it, it works too. You see, that's a convention. It's not, it's, if we asked them, well, what, in the universe, what is the correct side of the road to drive on? That question is meaningless because it depends on what country you're in. It depends on where you're at. Or how many, if I had a table that's, let's say it's 1 yard long or maybe it's 3 feet long, which is it? Is it 1 or 3? What's the right answer? Is it 1 yard or is it 3 feet? What's the answer, right? It's both, isn't it? Well, should the number be 1 or should it be 3? Well, you tell me what you want. You will tell me if you're using yards or feet, and I'll tell you what the answer is. The one-way speed of light is like that. We get to choose what it is, and that tells us how to synchronize our clocks. And then when you measure the one-way speed of light with your synchronized clocks, you'll find it was whatever you chose. Yeah. Okay? So the lightning bolt strikes exactly in between these two clocks, and we're going to decide that the speed of light's the same in both directions. We can do that. We're going to choose that, and then the two clocks are synchronized. But if you want to make a different choice, you can do that too, and you can synchronize them differently. That light requires the same time to traverse the path A to M as for the path B to M is in reality neither a supposition nor a hypothesis about the physical nature of light, but a stipulation which I can make of my own free will in order to arrive at a definition of simultaneity. We choose the one-way speed of light, and that tells us how to synchronize clocks. And that quote is by Albert Einstein. Einstein recognized that the one-way speed of light is not something you measure, it's something you choose. Which means I can choose it to be something very different than what most people do. In fact, I can choose the speed of light to be infinite when it's directly toward me and half c when it's moving away. And the reason I pick those two values, it has to average to c. It has to average to the speed of light that's the round trip speed. Okay, but you get to pick the one-way speed, and then the average will tell you what the return trip has to be. And it turns out it's 1/2 c if you make it infinite in one direction, because it's a time averaged. And one of the reasons I choose this is because it solves the distant starlight problem. But another reason is because all ancient cultures implicitly used this definition. They didn't subtract off light travel time because they didn't know what the speed of light was. When you saw something, that's when it happened. And so I'm going to suggest that the distant starlight is solved if we use this. I'm going to call it an anisotropic, which means different directions, anisotropic synchrony convention, or ASC. Using the anisotropic synchrony convention, light takes no time at all to get from distant galaxies to here. And according to Einstein, I'm free to synchronize clocks that way. And the distant starlight problem, therefore, is solved if the Bible's using that convention too. And so that's really the only issue. Is the Bible using this anisotropic synchrony convention, or is it using Einstein convention, or is it using something else? It's using some convention because it's talking about time. So there's some convention there. I think the Bible is using this anisotropic synchrony convention. I'm going to show you why. Well, I already mentioned one reason. All ancient cultures used that, and the Bible is meant to be understood by everybody, not just by modern physicists. But if you take a look at Genesis 1:14 and 15, then God said, "Let there be lights in the expanse of the heavens to separate the day from the night, and let them be for signs and for seasons and for days and years." And later we find this is the sun, the moon, and the stars also, the greater light, the lesser light, the stars also. He says, "And let them be for lights in the expanse of the heavens to give light on the earth." And it was so. It's that last little phrase, and it was so. What was so? Well, they gave light on the earth. You see, God created them to give light on the earth, and apparently they immediately did. And it was so.